Oh, we're being recorded. I forgot. So hey, I'm John Johnson. This is Parker Schmitt. We'll introduce ourselves in a second. We're having bourbon, lots of bourbon, and decided that the theme this year is the Matrix, right? And we got to talking about what if we're in a simulation? And it's not like the Matrix. I really don't believe in this, ever-ready copper top that human beings as batteries. That's a lot of BS. I think that, we probably can't know what alien motivations are if there was some civilization creating simulations and we're just NPCs. But we kind of went down, I better not lose that USB. We kind of went down that rabbit hole and thought this might be an interesting topic for us to talk on. And so we'll have introductions, we'll talk about, just the logical flow is, do we live in a simulation? Could we tell if we're in a simulation? What would be the requirements, the capacity planning for a simulation, the scale of the universe? We talk about the quantum world and the code that writes the universe. Can it be understood? Can it be hacked? We feel that as physicists, we would be the ones decompiling the code of the universe. So I'm John Johnson. I'm president of Docent, founder of CornCon, and I got my PhD in nuclear physics in 1992. I worked at Los Alamos, and I like bourbon. Parker?
So I'm Parker, founder of NetThunder, which is we're doing autonomous infrastructure, which primarily came from working at Fermi for a little bit, and the computing department never had time to go to lunch with me, so I was like, well, do some automation there was part of the idea. And I'm a physics, math, computer geek. Had a little bit of mentoring from Leon Letterman because he was a resident at our high school, and instead of being on time to English class, would rather do physics. So that was, sorry English teacher, but I'm totally not sorry. And so then, and I was the one who got John drunk enough to agree to do this talk, also during his own conference.
Yeah, shout out to Wes Diggs in the audience there, our bourbon connoisseur. He's picked out some really good bourbon. All right, yes. So in the Matrix, an advanced intelligence has figured out how to create a huge, fast, advanced simulation, right? It didn't evolve, but everybody felt that it was real. Have you heard of the uncanny valley? Right? If it's a little bit too surreal, then it makes you uncomfortable. So they have to throw in conflict and things like that. And of course, the people who have escaped the Matrix are now going back in to try to get people out. What they found was that the Matrix was code and that the Matrix was exploitable. So I think that the motivation aspect is a little bit silly in the Matrix, but it is a real question as to are we in a simulation, and if we were, could we even tell? And of course, would it really matter? It's not necessarily anything nefarious, but in a simulation, somebody might decide they can't pay their power bill and they just flip a switch too and we're gone. Not that we would know. So if you're familiar with Plato's cave, there was Plato came up with an analogy where he had people who were chained in a cave and all they could see were shadows cast from outside of the cave. And that's how they had to judge everything that was occurring. And so it's similar, the nature of reality is dependent upon, nature and nurture, our evolution, the way that our brains work, the environment that we have evolved in, and that's the way we see the universe. But that doesn't mean that what we're seeing is really the full picture. Okay, some of you may know that the brain also simulates reality. Are you seeing reality? Well, not really. The brain is there, and it's taking data from your sensors, right? You've got the 5 senses. They're sending electrical signals to the brain, and the brain needs to be able to interpret and pull all that stuff together to make sense out of it, and it builds a model of the world around you. In fact, we're not really seeing reality because our vision runs about 100 milliseconds behind the real world. So in order for the brain to be able to compensate for that, it has to anticipate. And it anticipates based on how your neural network of a brain has evolved and the weights and biases in your neural network based on the environment that you evolved in.
Even interestingly, in a physicist's brain too, it's always going to look like a simulation because math is the only real tool we have to describe the universe, and math is always going to look like code. So ironically, any theory of everything we have is going to look almost exactly like a computer program in a simulation because our brain is a computer in a simulation. So whether we are or not, it's going to look like one at the end.
Right. It could be indistinguishable. If it's not falsifiable, then we don't have a scientific theory. So we're looking for ways that we can start down the rabbit hole to figure things out. We're not here to give answers. We're here to just postulate and muse, and then go drink more bourbon and maybe talk more about it over that tonight. So Oxford philosopher Nick Bostrom postulates that there are three options in the universe. One is humans-like civilizations go extinct before they develop the capacity to build a universe simulation that's that sophisticated. Or number two, they can reach that, but by the time they get there, they have no interest in building simulations. Or they have the ability to create many, many civilizations. Once they figure out how to do it, they would create many, many civilizations. Let's say there are 100 or 99 simulations, and then there's what we call base reality. So if you're looking at the probability, is it more likely that you are in a simulation or that you're living in the base reality? It's more likely, if case number 3 is possible, that you're living in a simulation. All right.
Okay, so most standard models are saying looks like a simulation. So every time we make a model of something, like our quantum mechanics and the Schrodinger equation, it's easier for us to understand because we say, okay, we don't know what this particle is going to do. So let's make a guess. Just like if you are blindfoldedly hitting a hockey puck in a rink and it can bounce perfectly against every wall, best way is, hey, it could be anywhere. And interestingly too, in our limited reality, we're only going to have we might have an infinite number of correct, true standard models. Not the standard model we have, because we already know there's some things that are wrong with it. But we could have an infinite number of theories of everything. But in reality, what we have to do is we say, okay, here's a model. Does it predict something? Do we see it? And we'll get into it a little later, but one of the ideas behind neutrinos is in beta decay, there was an imbalance of energy. Conservation of energy would not hold. So physicists postulated, what if we just throw a fudge factor and make this particle called a neutrino pop up? And then eventually we actually found that those particles existed, and it kind of fixed everything. So we're always going to have these mathematical assumptions. We're always going to have it look like a simulation. I know when Sylvester James Gates said string theory is computer code, and everyone was shocked. It's not that shocking because we're just humans. And so let's go to the next slide so I don't cause feedbacks. But what John had brought up, and I thought it was brilliant, is he said, well, there's a high-res view of the universe, which we have, and then when you're in low-res, it gets a little fuzzy because certain things aren't stored in memory at that point. So it's more of a memory saving optimization. So for non-physics people, understanding quantum mechanics is way easier than you think it is because it's really just probabilistic math. And most people have done things, most people have done these things in this field. Random number generation, all normal. But making sense of it, we have this, physicists often like the Copenhagen interpretation. All that really is, hey, it's random. Until it interacts, it's random. Do we know why? Do we know who's throwing the dice? No. Which is very kind of computer-esque, but weirdly enough too, that would also potentially keep free will. So there's a lot of really weirdness and a lot of paradoxes that we will not be able to solve today. Maybe Wes can help, but it'll take a little while. But really the whole idea of scientists often say, oh no, if the tree falls in the forest, it makes a sound. Well, in the quantum tree and quantum forest, not necessarily. So you've all seen the particles, the beam splitting and the interference patterns and the double slit experiment, individual particles. If you throw a detector in there, you see 2 clumps of particles because you're interacting with them.
So I think that we have we have an agreement that we don't believe the interpretation that a human has to observe something for the wave function to collapse. We feel that there needs to be an interaction. There needs to be something interacting, right? There needs to be something. It could be two planets in a gravitational orbit. You don't have to have a human being there in order for that to be real. We don't, if we think in our world, yes, if a tree falls in the forest, it makes noise and we don't hear it. That can still be valid. And it's just to think that unless a human is there, which would be one way to think about a coded simulation, is if the NPC or the player isn't present, then that really doesn't need to occur, and it's computationally more economical to do that.
Yeah, and we'll even start showing that too, of memory saving, not needing to know the values. As we go there, we're going to have it look like a lot more like our universe despite our best efforts. So, let's see.
Yeah, I think the specifics that we wanted to talk about more than the motivations, right? I kind of alluded to that earlier, that we probably can't understand the motivations of an advanced civilization that is so sophisticated that it can simulate the universe, right? So trying to understand their motivations without understanding their psychology and the environment that they have evolved in is probably not very useful. But we have to think about what would it take? Is it something that we could feasibly do in our future as we advance, to have the technology to have, maybe leveraging quantum mechanics and parallelization we'll talk about.
And paravirtualization too. Quantum computing could be like making our own VirtIO driver on the guest that goes to the host.
Right, and we need to find analogs in order to find shortcuts so that we can create simulations without needing to have infinite computing power.
So there's actually some studies about limitations of computing power and a theoretical limit, and so it's by a matter of Planck's constant over the amount of over 4e is the amount of energy you would need for creating for the maximum amount of computing that you can actually do, below single electron transistors. Now, if you take that limit, and so you're saying I'm going to take all the computing we can do in the universe with classical computers, what could you probably simulate? Maybe a DNA molecule if you're lucky. But quantum computing could completely smash this. We also, if physics is a little different, behaves more like some of the UFOs we see, if they are aliens, if they are doing cool physics stuff. If you could slow down the speed of light.
Because they've figured out how to hack the code.
And then two, if we can't see inside a black hole, so they don't need to simulate those, they could be using their black holes for increased computing power. There are many ways that we haven't necessarily ruled out. We're going to try to rule out. I think one of the best ways we can try to rule things out is if the intelligent designer did something really stupid, like we can see atavisms in evolution, where you have there's stories of people who have grown fur and some other weird things that have happened. They're like, okay, clearly there's something going on. And so if we can show, there's something similar in the universe, we could even debunk that or...
Right, and an example of a hack that scientists have used is when you think about black holes, since you mentioned it, you have all the information in a black hole and everything that's gone in there, but you can represent that with the holographic principle, right? You can take and represent that 3 dimensions as a 2-dimensional. So that's kind of a way to understand without having to go to 3 dimensions. Now you've broken it down to 2 dimensions, and so those are the kinds of shortcuts that we might take in thinking of how to build a simulation that would be similar to what we might be living in.
So there's all these arguments. You'll see a lot of current physicists are like, no, simulation hypothesis, it's crap, and certain radioactive decay is hard to simulate, but we don't know. They're talking classical computers. And then we've also been saying on the kind of pro simulation is, well, neutrino oscillation would actually be easier to explain with a simulation because, hey, you don't have to store each neutrino flavor in memory. and you can quasi give the neutrino a little mass so that it can start oscillating. And the other assumption, we don't have to be real time. In fact, it'd be really easy if we could have future current events influence things in the past, which there's some quantum eraser experiments which say, yes, that can, with many asterisks. So time travel is still very hard, so I'm not gonna go into that, and that's a very hard thing. Doesn't quite rule it out, but kind of does in some ways. And so it's part of the idea of, oh, what about black holes? And then it seems like quantum computing and is a paravirtualization we talked about. Essentially, we're trying to, one of the hacking the universe is to get extra computing power might be, can we write a guest driver while we're inside the guest universe of our host universe or hypervisor universe, potentially. But we also don't know the driver running underneath, so it takes a lot of work, not that hard. And so I think the best way we can do this is start attempting to maybe create one. So that's the thing, we're gonna start doing that.
Right. So, what would it take to prove that we're in a simulation, right? Are there tests we can perform, observations that might give us at least a hint, a glimpse of the underlying truth there? So what would a glitch be? We might be able to demonstrate in a computer if you're overutilizing the capabilities of the computer. It's going to heat up. You're going to experience maybe a slowdown, a lag. And so maybe there are things that we can do that can force that kind of a state to be able to identify, maybe a lag, some kind of a glitch like that.
A race condition.
That's right, a race condition might occur.
Love it.
We don't want to blue screen the universe. People would be mad at us. And of course, having code that focuses the computational focus is on what you're focused on, right? You're looking over here. That's high resolution. Meanwhile, if no one's looking over there, depending on the rules, then maybe that doesn't need to be rendered because nobody's looking there. I imagine that when we developed telescopes, all of a sudden they had to increase their cloud budget. And so, we have to think in a simulation, a minority of matter forms life. Most planets don't seem to have life. If it is life, it's very simplistic, not even single-celled like bacteria, and sophisticated life, multicellular life, seems to be very uncommon. It took a very long time for that to evolve on Earth. And then, as far as we know, we're the only self-aware, sentient creatures on the planet that are, intelligent and able to look out and peer out at the universe and, try to understand how we got to where we are.
Poses an interesting question. Which is easier to become self-aware, Skynet or just a random bunch of physicists making computer simulation and humans show up?
So if we go low enough, which is really difficult, it requires a lot of energy to get down to the Planck scale. The Planck scale is about 10 to the minus 35 meters. And so that's from the size of a tree down to the size of the nucleus of an atom is about the same number of orders of magnitude as from the size of the nucleus of an atom down to the Planck scale. So it's really, really, really tiny. If you took a 20-pound bowling ball and jammed it into this little Planck cube, which we think is the smallest unit of space that you can have in a discrete universe, then you would have as much energy as we believe created the Big Bang. So we think that we're in a discrete universe, and quantum mechanics seems to point at that. And there do seem to be some discontinuities when it comes to gravity and quantum mechanics and being able to tie those together. That could just be our frail human minds as well, that we can't quite comprehend that yet. We don't have the math or the theories to support that yet.
Just to make sure with a discrete, so for everyone to understand, that means space is little points, not a big continuum. It's everything is done in integers.
Right.
So
when you get down to the bottom, it's space is not continuous. It's discrete. And time itself also has, there's a smallest unit of space possible, a smallest unit of time possible, and that's what Planck thought.
All right, so we can, I think we.
Oh, this was, yeah, this was me, I guess. So there are scientists who have, with their teams, developed some experiments with quantum mechanics to try to understand whether they could be in a simulation, maybe using a double slit experiment. There was another professor was focusing on strong interactions, and he feels that the equations for the strong force that holds together the nucleus of an atom are so complex they can't be solved analytically and require numerical simulations, and they're using shortcuts for that. I mentioned shortcuts earlier. If we don't have the computational power, maybe there are some shortcuts and some analogs that we can use to get us to a better understanding. And the shortcuts assume space-time to be discrete. The most advanced results have been a simulation of a single nucleus of a helium, but as classical computing hits a wall in the coming decades and quantum computing gets to show what it's capable of, that may allow us to really step up our ability to stimulate. Maybe both. Maybe both. I only have Diet Coke in here.
All right.
If we're in a simulation, we want to understand how would we code it, and that's what Parker's going to have. So I think if you think of the universe like Conway's Game of Life, anybody knows what that is, right? You've got rules. You know, this pixel is next to that pixel, therefore it's going to move in a particular way, or it's going to divide, or whatever. And so the universe seems to be discrete. It seems to follow rules like coding. And there's a syntax, there's a language that's used to make the universe consistent and run, whether it's a simulation or not. And so it is set up to be possibly be a simulation.
All right, so let's make one.
Where did I go? There. There we go.
Okay, so we're kind of some of the assumptions, and this is part of my when I can't sleep, what happens. Some of the physics that I kind of think about that led to this is, so fermions can never occupy the same space, and if you consider spin a dimension, so it's only you get two, so if you remember chemistry, the Pauli exclusion principle. So the way I like to think of it is every point in space is a kind of an unflavored particle, and so the universe we're going to first create starts out with just electricity. We're not even going to put magnetism in, but the results will kind of be mind-blowing because it might actually rear its ugly head back again. And so anything here is a Planck length. Now, why are there these connectors? Well, in our universe, those are kind of become like photons, so to speak, these connectors. And they're going to store values of these electric fields, which makes sense because in quantum field theory, it's, hey, there's a little bit of electric field there. It's discrete points, and in this point in space, it's a little bit electron, it's a little bit positron, it's a little bit up quark, and everything's kind of fuzzy. And if you have enough excitation, it becomes a particle. But we're first going to try to keep it simple, do a non-quantum universe, and see what happens. So we're going to, I just don't want to cause feedback by getting too close to the microphone, so hopefully.
Okay.
So this is the ideas of how can we actually decompile the universe, since our ideas of reverse engineering, which we're all good at that. So we need to figure out, do things have to be time dependent? We need to parallelize. And eventually we might want to unite all the fundamental forces, but we don't want to say, hey, they're all the same force, which physicists have done with electricity and the weak force, which is kind of interesting. But we are going to try to figure out, have some humanly understandable mathematics, and then switch it to more machine understandable mathematics, which is uglier for humans, but way easier to compute, because human math, we love continuous stuff, because we just look at one number, but computers hate it because everything's infinitesimally small, and so that gets to be a pain. So let's start making it. So right now, we're first going to skip the strong and weak interactions. We're going to try to add them back later. So this universe, we won't have atoms and molecules, unfortunately. Might create gravity later just for fun, because I want to say we got quantum gravity working, because it'd be kind of cool. And we're going to not even include magnetism. Ferromagnetism's not going to happen, because there's some cool stuff that happens in magnetism when you ignore that one little aspect, which string theorists have really taken crazy with the monopoles and stuff, and that's kind of our opinion on string theory. So let's make a physics. So to first get us in the right mindset, we're going to start with a 2D universe and a 2D grid. So remember that game when you're playing dots, like you try to make the boxes on there when you weren't paying attention in school with the person sitting next to you? Well, we're going to kind of do that. So the electric field equation, so physicists watching this, yes, I know it's wrong for our universe, but we don't have, there's no, oh, I should have an R there, my bad. So it's an errata here, so it is wrong for us too, my bad. So essentially, we have the electric field, but it's 2 pi epsilon naught, because circumference of, or the circumference of a circle, not the surface area of a sphere. And then the force is still going to be F equals QE, which is the charge times the electric field. We're going to have everything have a mass of 1, so the acceleration is QE, and we are going to be able to just do the linear approximations, because we know it's the second derivative of position. And so all the particles are going to interact with each other, and but here's the problem. It's going to scale as bad as cloud scales. Not the monthly bill part, because they scale the monthly bill really well. So have to poke fun at cloud. And so every time you add a particle, you have more interactions. How fast do they update? You're not going to update in real time. There is no way to simulate a universe that has an infinite speed of light. That's not going to happen. And so we're trying to calculate the field strength and everything serial too, because, oh, we know the acceleration. Oh, we have to do linear approximations for the position. Unless we had like symbolic manipulation in our computer, but those are way slower. So this is just going to get nasty, so we're going to make a new attempt. And this attempt will eventually actually be quantum mechanics. Will make things easier to compute. So I'm going to go 3 dimensions now, just because it's closer to us, and so there's some cool stuff that happens. So in 2 dimensions, there's 4 connections between each of the particles, or I call them the fermionic points, because they're kind of like fermions. There's forward, back, left, right. 3 dimensions, you just add up, down. And I'm going to ignore the diagonals, because that actually makes the computing easier. So this universe, proton, electron, but they're really like electron and positron, because they have the same mass. We're going to ignore the Higgs and just assume everything has the same amount of mass. And eventually everything's going to be discrete values, because then you don't have to propagate forever. If there's a proton a light year away, we don't need to calculate the Coulomb forces for that. That's stupid. It doesn't change anything, and in fact, likely that doesn't affect us too much here. So we're going to make a new model. So what we're going to do is figure out, so those points between the dots, those are going to store a value. It's going to be the field strength. And then each dot next to it is going to be the flavor of particle, or is there a positive or negative particle there? I might accidentally say proton or electron, but that's very wrong, because protons are made up of quarks. But this is a simulated universe, so who cares? We're just playing around, and we're playing God now. So intrinsically, we might say, hey, the probability of a particle going in this direction is proportional to the electric field strength in that direction. But there's a finite number of directions. So on a computer, way easier just to do that, because we don't have to worry about vectors anymore. We just say, hey, what's that individual scalar value, that individual number on that connector point to each of our points in space? So let's code it. So this is in a very CUDA-like pseudocode, Python-esque, because we were putting this together fairly last minute, because John had to run the con, so I didn't want to actually go through all of this. So
we really weren't up to solving the theory of everything quite this week.
It's going to be later.
This is. I forgot to give the preface, which is caveat. We've been musing on this, right? And this is kind of just some of our thoughts. This is not definitive. This is just the first chapter.
So this was our first attempt of coding something in attempt 2. So I'm essentially, because eventually we want it to run a lot like a GPU, because lockstep threads are amazing, no race conditions, and the more we can parallelize, the better, because if you have to serialize something that's at least the size of part of the universe, that sucks. That's more than sharding a database. Like, that's about the worst thing you could ever deal with. it would be easier to put all of Facebook on one database server than have any serialization here. So we don't want that. So, okay, so what we're gonna say is in each thread ID is gonna be a direction, because we have 6 of them, and we calculate a random number, and if that random number is high enough to hit that scaling and scale down to hit that factor above the probability that the particle goes there. So now we have a probabilistic setup, then the particle moves. And so we have the particle moving. What did I forget in this? Nice slide. We got to update the fields. When do we update the fields? What goes first? It's hard to go. Now we have race conditions hitting every point in the particle. So we're not on thread safe, even though we kind of did it in a GPU-like way. So we're going to take another attempt. So we want to, again, go kind of more like a GPU. We want to have everything propagate at the same speed. So tick, in a Planck time, things happen. Another tick, things happen. So it's all in lockstep, but every point in space can be its own thread or its own process. Really should be its own process because you want 0 interactions. And so what would the easiest way for that to be? Well, if a particle is moving, it has to do move operations in addition to propagate field operations. Well, let's make that the same speed no matter what. So if it does one move, when it normally has the quota of 3 things, then it can only propagate the electric field 2/3 as fast. And it would appear that time is moving slower for that particle. And oh wait, we just accidentally made relativity happen in our simulation that we were trying to keep simple. So if we go to the next slide, we are now saying, so in these ticks, and I'm calling them Planck times because they kind of are like Planck time, we're getting there. We're getting some ideas of our actual own universe, which is a motivation for creating the simulation, because we're learning a lot about this and figuring out, hey, this is kind of where quantum mechanics might be coming from, and little tricks from God. If we're not simulation, or what is God with simulation, that's a whole theology topic that I am not qualified to answer at all. And so we have
Give him enough bourbon.
Yes. Oh, there's a lot. That's got to turn the water into wine and then into bourbon at that point. So sorry about that. So really each particle is an object, so we're kind of object-oriented, but eventually we want to optimize it away. It's move, propagate, certain amount we can have. So now we're relativity. But what starts being, so we're seeing things move slower in time, all the relativistic stuff is happening. But what happens with relativity? I think we have the next slide.
Well, I was just going to say, water into wine, that could be one piece of evidence that we're in the simulation. Or in France.
So essentially now we are mostly totally parallel, because each particle is, unless the particles interact, they just move as they're supposed to, totally probabilistically, if they're not interacting. So you have to have some interrupts in there of when it interacts, which is going from the quantum world to the non-quantum world. So now we have that. We're starting to have collapsing wave functions, and we also have magnetism now, because except for some of the quantum mechanical parts of ferromagnetism, so physicists will say I'm wrong, but I also partially think they might be wrong because it's weird with magnetic monopoles, because magnetism just so beautifully comes from electricity. Once you change reference frames and add relativity to that, don't want to bore you with the math, but you can look that up. It's really cool, and Einstein actually came up with relativity at first, trying to figure out what magnetism was, because in some weird ways it made very little sense that such a thing existed. So we now are EMAG, despite our best efforts. And relativistic quantum mechanics just came there. So I kind of want to add gravity because we got special relativity out of there, and we now caveat, I did say we'll have some quantum gravity, but we haven't put in the strong and weak interactions. We're going to make some attempts later, so atoms are not working. So no, we don't have a theory of everything yet. So Wes, we still need your help. So the Einsteinian way to do that, except Einstein really wanted the changing speed of light, and Robert Dicke fixed that eventually. But we could say if there's mass nearby, that the interactions move slower and time appears to move slower. Problem with that, all of our race condition prevention goes away. So I kind of like to do it in the quantum gravity ways. I'm going to change that line of code in our attempt 1, and I'm going to add a scaling factor for the gravitational field, and then lower the probability of motion so that everything starts to slow down when it gets near a gravitational field. And that wouldn't fix our explanation of some issues with black holes, but it's at least a start to add some quantum gravity into this universe without destroying our relativistic thread parallelism that we end up getting. So now, I'm going to make an attempt to talk a little bit about the strong and weak interaction because I just want to see time so I don't know how much to talk about. Okay, great. So we need to, because let's try to look at getting some atoms in there because it's really cool and we can understand a little bit about the universe's computer or consequences of our algebra we're making to figure out a little bit about what's going on. So just a little bit of intro particle physics. So in a helium nucleus, think about how small that is. Those protons are pushing at each other 20 pounds of force. And it's so tiny you can't even fathom how small it is. That makes a hydrogen atom look giant in comparison. Physicists have rightly named that force or interaction the strong interaction because the only other name would be this ungodly strong thing that's holding these protons together. How does it even do it?
Yeah, have you heard of something called splitting the atom?
Or combining, that's why combining more yes. energy. That's why fusion's more than fission.
Fusion and fission release a huge amount of energy. The sun, right, is a big fusion reactor. And I mean, that's just all coming released from the strong force.
So rightfully named the strong force. See hydrogen bomb, that's just a little bit of the strong force happening. So I'll go to the next slide and I'm going to go a little bit into this because we're going to talk about neutrinos, neutrino oscillation, and is it an intelligent designer being stupid or a simulation? And unfortunately, the answer to a lot of that is maybe. There's arguments for both, and they're really cool, so we're going to talk about them and not come to any conclusions. So you look at a proton, so a proton looks like inside, and I'm going to quickly do this. If you have a physics background, you could ignore me for a little bit. And these quarks can be red, green, or blue. And just like opposites attract, unlike color charges attract. And so you have these three charges, and that's what makes these protons interact. But it has to be down at the quark scale, which is why that strong force is not very strong, or is very strong but doesn't go very far at all. As soon as you get apart from those atoms, you don't, which is why fusion is very hard, but eventually releases energy. And what's kind of cool about these is, let's say that green down quark, in a moment, in a quantum style moment smaller than the Planck time, it will switch colors. But that particle is always going to combine to be a colorless particle at the end. So it could be a memory saving technique because you don't have to determine which color that particle is until it interacts. So that's another piece. And then this is where all the neutrinos come in. So otherwise, electricity would make all the protons and electrons come together. So all be neutrons eventually. Well, that can't happen, so we have this thing called the weak interaction, which still is a nuclear force. So it's very strong, but we call it the weak interaction just because this is just so ridiculously strong it's unfathomable. And so the neutron will go into a proton electron and then an antineutrino. But then what it comes out, so in there, these points, just like our connectors between the grids, instead of photons, those are gluons. But it's a different connector, and so there's all these connectors between them in kind of our physics we've been working on from the simulation hypothesis. And so those have connectors, but those connectors have mass, which is really kind of weird and makes them decay. And so there's some weird stuff that happens which could potentially also debunk the simulation because the idea behind the Higgs gets really kind of fuzzy.
Just to say that we're macroscopic, we're big, and we live in a world that's ruled by chemistry. And chemistry uses these electromagnetic force interactions to bind together atoms into molecules and compounds. And so we are living way up here and really don't have any sense of, we can't make it personal when we get down to the scale of the nucleus because it's something that's just way out of any experience that we've had in our macroscopic world.
All right. So what's kind of interesting is these neutrinos, you saw there's a little subscript with the electron neutrino. And what that means is these neutrinos have different flavors. There's a muon, tau, and electron neutrino, and that's based on the particle they can create in some interactions.
Vanilla chocolate.
Yeah. So then I'm going to use the flavor term because in our code we just want to call it flavor for optimization. And so these quarks can have that red, green, and blue flavor. There's also anti-red, anti-blue, anti-green, but those are all antiparticles anyway, so that's just a Boolean. And so our trinary byte sizes tend to still make sense, because it seems like the universe is just this trinary computer, if it is a computer. We don't know. But what's kind of interesting is in that weak interaction, there's also this thing called the Z boson, which really does nothing except releases some energy. And so where does that energy come from? It's usually a neutrino ends up hitting that particle, and energy turns into these anti-neutrino pairs that just kind of fly around. They don't really interact with anything, so we don't notice them, but at Fermi, they're sending neutrinos to Minnesota to study oscillations. There's other experiments of just sending neutrino beams. So they really interact with very little.
Right, these neutrino beams go through the crust of the Earth in order to go through a lot of material, but neutrinos in general, there's a 50% probability that they will be stopped with 1 light year of lead. So it takes a lot to stop a neutrino.
Yeah,
but there's a lot of neutrinos, and so you have a huge trillions of neutrinos, but we get a handful in our experiments.
And then what ends up kind of cool there, back to the simulation idea. Okay, so neutrons are more often going to decay into protons. Protons sometimes decay into neutrons, and it's hard for a proton to like double decay, like W minus down to proton, and then again, except that also could create a Z boson, because it's, hey, I'm going negative, now I'm going positive, combine them, and then the Z particles tend to end up being their own antiparticles. And so what kind of is interesting is if you, in the simulation, just say, hey, I'm going to have a bunch of these things flying around and causing the weak interaction, it's way easier to code these weak interactions. And oh, this little bosonic connector is from our simulation, is seeing a neutrino's hitting it, so you better do some interaction and delete this neutrino next to it. And so that could be a way we could weight those probabilities. Because otherwise they seem like, why are we computing all these neutrinos? I think we go to the next slide. But then there's also, so sort of saying, it could be just this nice little fudge factor for all these decays, because you have these weighted averages. But neutrinos, they oscillate, and that's why we think they have mass. Now, we're pretty sure they do if relativity is right, because they're going between electron, muon, tau. In reality, if you're going, or not in reality, in simulated reality, we end up seeing, oh, well, neutrino interacted. What kind of neutrino is it? Let's guess what it was. Now we no longer have to store that in memory. All this stuff in memory is now stopped, which I know is like not a bit, but a trit, I guess. I don't know how to say the trinary bits, but they add up a lot. So this saves a lot of memory after
a tribble.
Tribble. Okay. And so, well, it could maybe create these weighted probabilities and at least save some memory when we're creating all of these. So it's a little bit of initial brainstorming. So we have these red, green, blue. It's similar to how we did the electricity. I'm sorry, the Coke keeps going in the way. Apologize for that. And so we can have these just anti-neutrino pairs pop up. Hey, there's a little energy decaying. They just come up, and it's an easy fudge factor. But gravity slowing down the speed of light, we've shown a way to do that by lowering that probability. And so another few fudge factors, and this is just total speculation, so physicists, outside of here, we have not looked into this too much, but hey, we need to get these galaxies to hold together, and so it might be interesting if every once in a while there's a little bit of extra mass fields just randomly there, and have a little bit of a fudge factor, which would look exactly like dark matter. And then, we don't want everything to collapse on itself, so let's just start pushing everything apart and adding this thing called dark energy in there as a fudge factor. What's maybe a debunk of the simulation is the cosmological constant is not constant everywhere, so there could be something that's driving that. Now, to not burst the bubble of simulation hypothesis, that could also be, it's calculated from something, and based on the total mass, that's how it gets its numbers, so that it can be changed at certain points without really worrying about that. We don't know enough. If we're at the point where we can simulate a universe, we're trying to think at the level of a crazy advanced civilization. But I think we have that trinary processor. And The non-computer explanation, though, of this trinary processor is, think of a three-sided die. Think 2 dimensions, think of a triangle. That's what the three-sided die would look like. That could look like a higher dimension that's a really, really tiny. And so there's other ways to explain things like that. So that's not like, oh, it's proof it's a computer. It's, okay, there might be a tiny dimension with just a few bytes, and it will look like a computer. So we don't really, it's hard to really know the difference between that. And so, but we were also, one of our conversations, John and I were talking, said, oh, the Z boson, that shows it's not a simulation. Oh, wait, no, that makes it easier because trinary, and you still have that value, so make that a lot easier, and yeah, you would definitely observe Z bosons. So we thought we had it, and then we didn't have it. The Higgs might help debunk that too. Yep. So, and that's kind of what we're thinking is the Higgs mechanism, which is we can explain where a lot of mass comes from, and that is fairly complicated, and electroweak is also really a complicated process that does not necessarily look memory saving. Why would you say, oh, only at certain energies make electricity and weak interactions the same, unless you're trying to avoid a divide by zero somewhere, and then, oh, at this energy, let's just change this and can make that easier because they know that people like us, annoying people like us, might make particle accelerators, so they might have to do some stuff and keep things interesting for us. And they're like, oh, okay, we see that energy, we can observe a civilization. Should have just thought about that. That's how you'd find out if there was intelligent life and you were self-aware is, oh, crazy amounts of energy here, let me look. Oh, okay, they're figuring this out, kind of cool. So that might actually be intentional. Who knows? So that's, it's really kind of hard to know all of these things, and I think we figured out what the point of a neutrino was, but it still seems like there's a lot of computations that you'll have to do. So we just, but the main big point of, oh, we might not be, is how big would that computer have to be and what would you have to do to make it, is the really, really hard question. But again, paravirtualization, there's some stuff we could, so we can't rule it out, but that makes it really hard. So let's hack some stuff, or at least talk about it, because we're way before we can do that. We don't want to mess with the universe. So, because I want to go to CornCon next year, and we also go to CornCon next year. So then,
we're just kind of, you know, what's the journey that we've taken this hour? You know, we've kind of defined what a simulation could be, thrown out some ideas of how we might come up with a simulation, how we might save on the computing power so that we could simulate more and at least understand what is possible, or maybe what the underlying rules are that we're dealing with. Because if we understand what the rules are that we're dealing with, you know, my question is then, can we as physicists, if we understand the code, can we hack it? Can we identify glitches? Can we identify vulnerabilities? Can we exploit it? Can we now travel faster than the speed of light, right? Can we now tunnel through space great distances and do these amazing things that are only in the realm of science fiction? And so the math and physics of the universe need to be way better understood. You know, compared to an advanced civilization, we're an amoeba, we're an ant. You know, we're just a very simplistic, we get smarter with bourbon though, so, but we need to find what can we do, what can we observe, what can we create in our own labs, our own simulations that will lead us down the path to better understanding our universe so that we could do something like this. You know, can we hack the universe? Can we expose glitches? Can we enter God mode, right? And I think that if we can do that, you know, we're starting to peer out at our creators and understanding how the universe works is understanding how they coded the universe that we're in if we're in a simulation.
So, and also for like a non-nation state actor, as we put it in security terms, is we have to think about what would we want from our hack, right? Because one of the big criticisms we've all had, especially at a lot of financial institutions, are like, oh, what do we need to patch? Where are our vulns? Instead of, okay, red team, go steal some money. Go steal some stuff. So, what do we got to steal? We're gonna be attackers. Energy and matter is really nice. Like I said, we can make whatever we want. And so one thought behind the Fermi paradox really comes from Dyson spheres. Why don't they exist? Why aren't we seeing stars dimming over time and evidence of this? Well, maybe it's unnecessary.
You all know what Dyson spheres are? When an advanced civilization is advanced enough that they can consume all the energy from their star. So they build a sphere around it so they can collect all the energy from their stuff.
Yeah, that's one's right there. And so it'd be so much energy from that. But if we can also change the speed of light, control gravity, then which some of those descriptions of some of those UFOs or UAPs at military bases do. Now, we don't know enough to say, okay, they're definitely alien or not. That's a very hard question right now.
No, I've spoken to Richard Thiem, and they are.
Okay. I think there's a good probability that they are, because I'd be like, okay, if we're at that advanced civilization, let's program some drones. If we see some cool military stuff, let's see what kind of tech other people are making. That's what I'd be interested in. So, I mean, it makes a lot of sense, and I don't want to interact with these ants because we want to see what they're doing. Like, hey, you can observe a caveman, but when you want to have a conversation with them, you might get clubbed in the head.
Well, these could be the daemons of our creators, right? That they have things in here watching us that don't necessarily, they know the code, so they don't have to obey the code. I mean, they have to obey the code, but they know how to cheat the system, right? They have God mode.
Yeah, could absolutely be that. And so we can, but the other thing from this, do these principles matter if we're not in a simulation? And the answer, I think, and John thinks too, I think we've talked about this, is yes, because we're creating these models anyway. We want to figure out ways to cheat the system, so we got to still do our reverse engineering and find ways, because we really say as hackers is we just know more about how the code works than the guy who wrote it. You know, someone says this function does this thing. Oh, but it also does this other thing. Oh, no, it doesn't. It's like, yeah, the way you think your code works, but the way it actually works is a little different. And that kind of thinking is what we need anyway, so it almost doesn't even matter. It's almost, hey, let's bring our mindset in the physics world, and there's some interesting combinations in our fields with the physics field, and there's just a lot more to think about, and hopefully we'll get to do a little bit more of this in the future.